So nucleophilic substitution has two different mechanisms. There's the SN2 mechanism, and now in this video we're going to talk about the SN1 mechanism. So the S and N stand for substitution and nucleophilic, and the 1 in this mechanism stands for unimolecular, which is going to refer to how many molecules are involved in the slowest step of this mechanism, otherwise known as the rate determining step. So that implies also that this mechanism has more than one step. So it's a bit misleading. The 1 term is really not particularly helpful for remembering the mechanism, other than remembering that it's counterintuitive. Okay, so our reactants here, we've got hydroxide, that's our nucleophile. I've got 2-bromo, 2-methyl butane. So we want to give a quick sketch here first. The bromo, and there's another methyl here. And so that makes this a tertiary halogenoalkane. And so SN1 is the mechanism that tertiary halogenoalkanes will always undergo. We said primary will undergo SN2, tertiary will undergo SN1, and secondary can undergo either. So if I want to try to summarize this structure down, and if I think about what's attached here, then I maybe will draw this as C2H5 just to make things a little bit more concise in my mechanism. So I'm going to move that off to the side and shrink it down. Okay, so if we get started, we've got our nucleophile. I'm going to draw on those lone pairs. I don't have to draw all of them, but I have to draw at least one because I have to show the curly arrow originating at a lone pair. And it's going to react with our halogenoalkane. So I'm going to draw the bromine going this way, away from the nucleophile. I'm going to draw the other 3 things sticking out. It doesn't really matter how I do that. I'll do the C2H5 up here, the CH3, and the CH3. Really important that I always show the bonds between the carbon and other things and not the carbon and H. Okay, so in the first step of this reaction, I realize now that I've drawn both things, I actually have to remember that it's SN1. And really what SN1 means is that both reactants are not involved in the first step. The first step is unimolecular. Only one thing is involved in the first step, and that's the halogenoalkane. Now, obviously, there's things in the container, in the reaction container, and things are going to be colliding with one another. But there is evidence, there's rate data to suggest that the first step of this reaction only involves one molecule, and that's the halogenoalkane. So I'll give some more follow-up information on this in class, but for now, you need to accept that the first step only involves one molecule. And so what happens is they believe this bond breaks before any other bonds form. So in our first step, SN1, first step, 1 arrow. Okay, and that's going to lead us here to what we call an intermediate. Now, intermediate is a little bit different than a transition state. We're looking at distinct steps of a reaction. And I've got this intermediate, and I'm going to show it formed in the first step, and then I'm going to show it get used immediately in the next step. Now, the other 3 things haven't left this molecule, so the CH3s and the C2H5 are still attached to this molecule. What is no longer attached at this point in the mechanism is the Br. And the Br has left with that those electrons in the covalent bond, so now the Br is minus. Well, in terms of conservation of charge here, if I look at this reactant molecule, there's no overall charge. So if the bromide left and is now negative, that means what's left behind must be positive. And you can see that right here we've got this carbon, and the carbon only has 3 bonds. It's actually missing, there's missing electrons here. So this thing here is called an intermediate, and it even has a more specific name. It's called a carbocation intermediate. So carbo, carbon, cation, positive ion, and it's an intermediate. So these show up in a couple of different mechanisms where you have a carbon species that has an overall positive charge that's formed partway through the reaction. So this is step 1 of the nucleophilic substitution mechanism. Okay? Now it's an intermediate. So in step 2, we're going to use that intermediate in step 2. So I'm going to redraw it. And now is when the nucleophile is going to come into the mechanism. Usually in the next step, I can get away with sort of drawing it without the brackets. So I've got the carbocation here, and I've got the OH, the nucleophile. And I do need to make sure that the curly arrow gets drawn from the lone pair on the oxygen to the carbon. Any of these lone pairs will do. Can't draw it from the H, though. I have to draw it from a lone pair going to that carbon. Now you can see that this intermediate is sort of trigonal planar in shape. That means it's flat. And so really the O, I could draw it attacking it, bonding to it from any direction, because now that it's flat, it can form bonds from either side. But the way I've drawn it here is just fine. And when I do that, these curly arrows either show bonds breaking off, like it did in the first step, and now we're showing a bond forming. So we're going to show the bond that forms between the oxygen and the carbon. And so afterwards, I've now got OH here. I've got C2H5 here, CH3 and CH3. And so that's the overall SN1 mechanism. It has two distinct steps. The first step is what's known as the rate determining step. This is the slowest step, and sometimes they write RDS, rate determining step. So that first step only involves one particle. That's why it's called SN1. That's where this 1 comes from, unimolecular. In the important slow step, there's only one molecule involved. So the bromide breaks off first. We have a carbocation intermediate, which then gets used in step 2. That's when the nucleophile donates its electron pair and forms the alcohol. So I began with a tertiary halogen alkane, and I end with a tertiary alcohol.